Okay, well, welcome back. And as I said earlier, we are going to take off in a very different direction this afternoon. We're going to try a very different approach than any of the machine learning techniques we've tried earlier. We're going to look at some very different applications. However, we'll find some of the principles that we discussed earlier arising here very naturally and very centrally to a lot of the things we're going to do. So deep learning, it's no surprise, is a very, very hot topic these days. As a matter of fact, many of you, I'm sure, are coming motivated because of the fact that it seems to becoming so important to the sciences, in particular for a lot of you, to society in general, with so many applications, important applications that have been enabled by deep learning or neural nets to synonymous terms. I think you'll see how they're synonymous as we step through the mechanics of what makes a neural net. The two pieces I mentioned briefly earlier that really enable this stuff have resulted in the emergence of this technique, its dominance in machine learning, are the widespread availability of parallel computing on the desktop in the form of GPUs, along with big data training sets, large training sets, which these learning techniques require. So this is what's really changed and enabled a technique that we'll see goes back to certainly the 80s. Most of what we're going to do today theoretically resembles what they were doing in the 80s, but in practicality, our ability to implement it with large and powerful networks and train those networks has only become possible in the past 15 years. But again, when we look at the specifics, we'll see how these two components are important and necessary to make neural nets work, and how they've only become available at this level in the past 15 years or so. There are two perspectives you can really take on the foundations of neural nets and why they look like they do. You can either think that they're inspired by biological models. We're trying to model, as the name suggests, neurons in our brains. Or you can look at them as this inevitable evolution of classical machine learning techniques going back to simple classifiers, linear classifiers that people were working on in the 60s. And they're both fair, and they're both useful ways to look at things, and they both remain important perspectives today. We still derive inspiration from biological models for new improvements to networks. That'll make more sense as we look at how these networks are really architected. And certainly the foundations of machine learning are important in understanding how these things work. And we'll see the principles that we've started to understand with our earlier machine learning topics arise again here. So we'll see the deep relationship. So they're both good things to keep in mind as we move forward and look at how these things work. If you look at things as modeled after the brain, you'd start out saying, well, biologically, if we look at the histological slides under a microscope, brain cross sections of humans or any higher organism that's got a brain, we notice that we have a bunch of neurons connected together by synapses. It seems like learning is the development of those synapses, or their pruning, and that's what really characterizes the intelligence of these networks. So we might try to capture this as a graph of how these things are connected together, one layer or one neuron to the next. And if we did that, we'd quickly find ourselves representing these connections as maybe a matrix of weights of the strength of those connections. And so you'd very quickly find yourself just using, again, the techniques in the language of linear algebra that we talked about earlier in machine learning, how useful it is. It remains true here as well. It would just naturally emerge from trying to model things biologically. Likewise, if we started out thinking of just machine learning problems, and we said that, for example, we wanted to develop a classifier that would be able to separate dogs and cats. And so based on the characteristics of dogs and cats, and we'll evolve this into something that could look at pictures and photos of dogs and cats and be able to distinguish between them. We might start out with a very, very simple mechanisms to do this, and a linear separator like the perceptron was something that was back in the late 50s, early 60s, was considered to be the technique, simple technique, but very limited technique to do this kind of classification. As a matter of fact, the limitations of this early model were well understood, and for a long time it was considered to be a fundamental limitation that would limit the applicability to doing useful applications. Turns out that was mistaken, even theoretically, and is very misunderstood. At any rate, these things have evolved today to where with our modern network, we can take data sets that are very difficult to separate. So if we look at this red and this blue curve, for example, they might represent some kind of data set where things are a little bit entangled here, at least the point where we can't just draw a clear line between them. Instead, they have some entanglement that requires us to do something nonlinear in order to separate the two. And we'll find that one of the characteristics, maybe the defining characteristic of neural networks, is that they have a nonlinear capability built into them that allows them to do operations, to allow us to take data sets and to stretch and twist them in such a manner that we can pull them apart, even when they're relatively entangled. So we'll see exactly how this works. So again, this is the second perspective, looking at things just from an algorithmic point of view. Okay, let's look at what the basic neural net architecture is, because it's not difficult to understand. As a matter of fact, in about 15 minutes from now, you will understand entirely, fundamentally, the building block that makes up a neural net and exactly precisely how it works. The mathematics of these things are very simple and straightforward. It's only when we start putting together and seeing the emergent behavior that it becomes complex, very, very much so. However, at the basic level, it's very simple. We have input layers where we input our data, and these might be pixels from an image, or they might just be numbers from some kind of regressive thing. We're trying to predict stock prices or whatever. Whatever our data is that we're inputting goes in the input layer, and our output layer gives us results. And they might be numerical values in particular that we're interested in, or then this might be a neuron that lights up if this is a cat and a neuron that lights up if this is a dog, to separate classifications. But in between, we have the hidden layers. These hidden layers are what make these things deep networks. They can have depth to them. We can have many hidden layers here of varying width. And this is the deep learning aspect of it. That's why deep learning neural nets are synonymous terms, essentially. So these simple networks right here can just be built up into very complex networks, which is what we'll do, and we'll get great power in our applications. But in practice, this is what it looks like, is we have inputs on this input side. And again, it might be something like a photograph right here, where each neuron gets one of the pixels from this photograph. And the output side can be many different things. They can be discrete possibilities like, what is this photograph showing us? Is it a woman, a house, an airplane, a cat? Or it can be more complex things like a transformation of the image, segmenting into its different parts or transforming it into a different style. And we'll see how to do these kind of operations as well. Now, how deep are these networks? How wide are these networks? These are all hyperparameters. Once again, hyperparameters are going to be an important part of us developing and making these models work. These are hyperparameters that we get to choose and select. The depth and the width are going to vary tremendously. We'll see with different architectures, and we'll see why we might vary them in certain ways. But let's instead at the moment focus on the actual building block itself. So let's look at the small little pieces that make up these larger networks. So the input sides we give some values to. Again, these could be pixel values from an image. The intermediate layers are going to acquire some values themselves by doing some simple math on these input values. And they're connected to these inputs with varying weights. These weights represent what the network's capable of, what it's learned. As we train the networks, we change these weights to make the network do the right thing. But let's assume we've got a working functional network here that's been trained, so it's doing its thinking already. This is called the inference or forward step. It's where we've got a network that's trained. So we now expect to give it useful data, real data, and expect to get useful outputs. So this inference part of the network, as opposed to the training where we're trying to figure out how to find these weights. We'll find out that's the hard part, but let's assume we've got a working network. So in the inference step, when you've got a working network, you throw the data at it, and then each layer calculates its own values based on its inputs from the preceding layer. And it uses the weights of the connections to the preceding layer's inputs in order to weigh how much it should input each one of these. And it has weights connecting it to its succeeding layers as well. So these weights are just floating point numbers here, positive and negative. They can go from negative infinity to positive infinity. And we'll find ourselves essentially representing these as nice matrices to sum them up, but we'll get to that in a couple of slides. On the other hand, there's one more part of the math here, which is where these networks become really interesting, the nonlinear aspect of them. And I'll explain to you very explicitly why this nonlinear part is important and exactly what capability it adds into the mix. But at the moment, just be aware of the fact that we do need some nonlinear function in our mathematics. Linear algebra is, as the name strongly suggests, linear mathematics only. So if we just do adds and multiplies from one layer to the next with these matrices, there's no possibility, there's no way to introduce a nonlinear type of operation. And we need this, as again, we'll see very explicitly with a couple examples I'm going to show you where it comes in, but we need this kind of capability, this flexibility to do some nonlinear operations. The classic nonlinear operation used for for many decades in machine learning was this nice smooth sigmoid function. And we'll see mathematically later on when we try to solve these problems. It's nice to have functions that are smooth and have nice differentiability, maybe that are bounded, only go from between 1 and 0, for example. That's a nice way to represent a probability, certainly, right? So for a long time, all things being equal, people liked a nice smooth function like this as an activation function. However, over the past 15 years, as neural nets have evolved rapidly and acquired a lot of attention and a lot of research efforts gone into it, the nonlinear functions have turned into what seemed to be, at first glance, some cruder, more simplistic things with less desirable characteristics, but they empirically are giving us much better results. So first of all, that's the empirical results drive deep learning more than anything else these days. You try things and they work or they don't work, and it turns out that some simpler functions work much better. But there are some justifications for it. So at the moment, the most popular class of nonlinear function are these rectified linear activation functions, which are simple functions that look like this. It looks like a linear function, a normal linear function, except you have a cutoff at 0 where anything that's negative is just 0. So this looks mighty close to being a linear function, but it's absolutely nonlinear. Anytime you've got kind of a discontinuity like this, kind of an if-then, if it's less than 0, 0, it's nonlinear. So this is absolutely unquestionably nonlinear, even though it's made up of these two nice linear pieces. Now, this rectified linear function is, as I said, at the moment, the most popular class of function, even though, it doesn't always deliver us some nice bounded value between 0 and 1, and it's not real nice, smooth derivative and everything. But at the end of the day, it is easier to calculate. It's cheaper to calculate than you can imagine a function like this. It's good in recognizing the fact that we're starting to understand that networks, neural nets in practice, can be very sparse. The connections can be pretty much 0, weak connections, or stronger connections, lots of 0 connections in networks. Reflects, again, not only biological networks where they get pruned down a whole lot, but just the empirical results we find with networks. That works pretty well there. It's easy to calculate the gradient of this derivative of this. So anyway, it's got some good characteristics. And at the end of the day, this at the moment happens to be the most popular nonlinear function that we mix into our math. It also has some variants of it, leaky and noisy ones, which this isn't strictly 0. This might be a little bit non-zero here. We introduce some noise into it. But this general class at the moment is the most popular activation function. Okay, well, where does that fit into our math? Well, it fits into our math by just applying it at the end of our simple-minded linear calculation. So let's step through that right here. So let's say these are our inputs. This is our intermediate layer right here. How do we get to these results right here? Well, to get to this, say, 0.13 value here, this neuron is basically taking all these 3 input results and weighing each one of them. So it's taking 0.5 and weighing it by the appropriate weight for its connection, which happens to be 1. Then it's taking 0.9, weighing it by its appropriate weight, which is -2. And then 0.3 and its appropriate weight, which is 2. And it just does the simple math, adding those together. And then after it's done that, then it applies the nonlinear function. And we'll say the sigmoid function in this case here of the choices we have. So it applies the sigmoid function and ends up with 0.13. And that's how we get this result here. Likewise, this result here has similar mathematics, and likewise this one here. Very, very simple, straightforward mathematics. And we can continue and do the same operation to get the results on the output layer right here. It's the same type of mathematics. We take these 3 inputs here, weigh each one of them appropriately, add them together, and then apply a sigmoid function, and we end up with this result of 0.35. So it's very, very straightforward, simple mathematics. And one can very quickly imagine that this not only represents itself well as a matrix operation, but indeed, should be represented on a computer by matrix operation, where we have a matrix of the weights, the layer weights, and the inputs, a simple vector, right? It's a one-dimensional bunch of entries here from one layer, not only on the input side, but from one layer to the next, we've got these vectors. And so we can look at this as a vector matrix multiply. And then when we're done, we've got a vector out of it, and we can take and apply the sigmoid function to each one of those results, and boom, we've got a vector to go into the next layer. So it's very simple. Now, this also, if you are familiar with GPUs at all, if you say come to one of our accelerator workshops and learn to program GPUs, you would say, oh, this is obviously very efficient at pumping through a GPU. If you're not familiar with GPU programming, you may have noticed, though, that deep learning seems to be running on mostly GPU-based hardware, and that indeed is the case. And as a matter of fact, it's one of the widespread reasons for the rapid adoption of GPU hardware everywhere. And this is the case. GPUs are very, very good at simple linear algebra operations like matrix vector multiplies. They're extremely effective and efficient, and consequently, on GPUs, we can pipe through these operations so quickly that they become the irresistible type of hardware to use. Now there's one last little piece of math to add into this algorithm here, and then we're pretty much there. We've got the actual real world network thing, and that's a bias. We'll find it's also useful for reasons I can illustrate, and I will in a slide or two. It's useful to kind of be able to center our functions or slide our results around somewhat, to normalize them from one layer to the next, to, at least to slide them around and keep them. You could think of it as it's nice to keep your results centered around the middle of that nonlinear function. Maybe you like to keep them there in the interesting part of that nonlinear function. Maybe you can think of it as it's easier to learn if things are centered at some reasonable values. For example, as I'll come back to it with pictures, if we're showing somebody pictures of different things to try to teach them what they are, it's nice if all those pictures are kind of white balanced. They're at the same level. They're not all really dark and some are really white, washed out. Instead, what if all the pictures are kind of nice and in the middle and easy to interpret? It's easier to understand what you're looking at, right? Biases kind of help us with that, keep things centered. So the bias math is extremely simple. After we do our vector matrix multiply and we have a result, we add a bias to it. And there's usually one bias that's the same for the whole layer. We add that bias and then we apply the nonlinear function. So that's our math for an actual real world network layer, as we do take the inputs from either the input data or the preceding layer. We multiply that vector by this matrix, which captures all the weights. And then we add a little bias to it, and we've got some results we can then stick into our nonlinear function, and then boom, we've got the results for that layer, which we can now pass on to the next layer. So that's the entirety of the mathematics. Let's see, I don't think we have any pending questions on this. Good, we'll move forward then and see how this actually functions. Now here's what's actually going on with our data. This is two-dimensional data. If we input in a couple of neurons input, this is what happens with these operations we just discussed. And in this animation, when it starts out with a square grid, you can see that the first thing that happens, well, we're on the warping phase right now, the square grid, is it skews some. These squares become kind of diamond shaped. And that kind of skew and rotation is what matrix multiplies do. Then you can see it's sliding right now, translating. That's what a bias does. And at the very end, when the lines start to bend, that warping, that operation can only be done with nonlinear functions. So all the matrix operations in the world can't bend these lines. It can skew them like this. It can slide them around. It can scale them, but it can't warp them. That's why nonlinear functions are so key to what we're doing here. They give us this warping ability, which we'll find is really useful in trying to move our data around in important ways. So this right here sums up the operations, exactly the operations that go on with a network layer from one layer to the next. We've got our rotation and skew and scale from the vector matrix multiply. We've got the bias giving us this translation, and we've got an activation function that gives us the warp. So keep this picture in your head. It won't mislead you in the least, and it will give you a very good idea of what's going on as we do these mathematics. Now, the reason these operations are so useful is we can take now data sets that are entangled and separate them. So what we have going on in these two animations now, the one on the left is us actually succeeding in separating some entangled data. The one on the right is failing. So it's what happens if we don't learn how to do this stuff properly. We have all kinds of operations we can do, and we can certainly, it's not inevitable that things work out. But the one on the left here is where things are working out. We're starting out with these two red and blue spirals, and they're pretty entangled. To draw a line between them and say, hey, all the reds on this side and all the blues on this side is impossible when we start. But our ability to warp this sheet and to stretch this sheet out gives us the ability to actually learn to distinguish between these two. And what you are seeing here is an animation of a network actually learning to distinguish between these two things and end up with the final weights that can do the right operations. So at the end of the animation here, we can clearly distinguish between the red and the blue. We have a network that's smart enough that if we feed it the input data, it's separated the data very clearly. Now, how do we find this right network weights? Well, you're seeing it learning here in action, and we'll look at how that algorithm works. But at the end of the day, the algorithm has learned to separate things cleanly. And it can do that because it can do these rotations and these skewings and these scalings, and most importantly, these warpings that are required to do this. So this is, in your head, again, a picture that won't mislead you as to what's going on with the network. Now, you might say, okay, that's great for those spirals, but what about other data sets? For example, here's a data set. This one's going to be pretty hard to stretch your way out of and warp your way out of, right? These two categories of things, whatever they are very entangled. Well, It turns out that if we get a little more creative with our thinking, we can do this too. Here you're seeing an animation from a couple different perspectives of that bullseye pattern where the red in the middle is being stretched out in 3 dimensions instead of 2. So we've taken our 2-dimensional rubber sheet, but now we're going to operate on it in 3 dimensions. So now we can take that sheet and we can push that middle red section out enough that we can cut it off like we see here. We can now draw a clean line between the two. So you're seeing that sheet as it's learning how to stretch it and deform it. So we can draw a clean line between the two. On the right here, you can see where it succeeded. This network is very good now at separating the bullseye center part enough that it can draw a nice plane, hyperplane in higher dimensions between these and separate the red and the blue. So you are seeing in action here what networks can do because they have this, linear algebra matrix operation, vector matrix multiply combined with this little nonlinear operation at the end. It gives it tremendous power. Now, you're also seeing something I think a lot of people aren't aware of, which is that the width of the network is what determines how many dimensions we're actually working in. And so if we have a network that's 3 units wide, 3 neurons wide, it's got 3 dimensions. It has the capability it needs to be able to do an operation like this. And the width corresponds to exactly the dimensionality things are working in. And you can see we're working in higher dimensionality here can be very helpful in allowing us to separate data. So these things are related in ways that are pretty simple and understandable at a fundamental level. When we build them up, it becomes very difficult to understand things specifically. So keep these pictures in mind, the principles that are involved. And again, it won't steer you wrong. So how about this problem right here? This one seems even trickier and more intractable. But if we think in 4 dimensions, which is a little bit harder to do, in 4 dimensions, these two things can be warped and separated just the same as our 2-dimensional rubber sheet in 3 dimensions can be separated. So in 4 dimensions, we can certainly stretch these things apart so that we can draw a hyperplane between them and distinguish between the red and the blue very easily. So that's the power of neural nets. Okay, now theoretically, what I've said is that these networks can do anything, right? Or I've suggested it at least, and now I'll theoretically tell you that's pretty much true. They in theory, they can do anything. That's the universal approximation theory. It tells us that even one hidden layer network can do pretty much anything. I mean, the formal way of saying it can approximate any function given enough width. And we can make the network have as many dimensions, as wide as we want it to be, as many neurons as we want. And saying you can approximate any function is a way of saying you can do anything, because a mathematical function can certainly take in a bunch of values that represent the pixels of an image. And a mathematical function's output can certainly light up a pixel, ones or zeros that represent what it's viewing. So that's a way of saying, for example, a mathematical function, the right function, can recognize any picture. And it's exactly what you can do. If I give a mathematical function that can do anything, then I can set it up to recognize pictures. I can set it up to recognize tumors. I can set it up to recognize words from a wave file that represents speech. So this is a very, very powerful statement. Now, the reason it's not actually that interesting is that the width could be enormous, to deal with this. And we still haven't yet figured out how to find the correct weights. So just saying that you can have this network doesn't tell you how to find the weights to make it do any function. And that indeed is the problem. So let's talk about how we find these magic weights. And this is the training side of it. The training side of it is where Tensorflow is going to do a lot of heavy lifting for us. It's going to make these things black boxes. As a matter of fact, I could frankly just wave my hands right now and say that, the network TensorFlow will use backpropagation and stochastic gradient descent solver to just find the appropriate weights. And that's pretty much a one-liner in TensorFlow, and you don't need to worry about it. We can pick a few different parameters, and I could leave it at that. Alternatively, but I don't want to do that because we can understand, what's going on here a good bit more. As a matter of fact, if I had an extra hour today, which I don't have, I could step through step by step the mathematics of this backpropagation algorithm I'm about to describe and show how it works. It's not that difficult. And I'll point you to a couple resources for those of you that want to look at a nice half-an-hour video and understand it. It's not difficult, but I'm just going to give you the very quick top-level view of it. But the particular details are not that difficult to understand. It's just simple. It's no more than first-year calculus is the mathematics involved. Basically, the chain rule from calculus applied cleverly. That's all backpropagation is. So it's not that hard to understand the details, but I don't have that half an hour to an hour to digress. And many of you wouldn't even care anyway. You're happy to let TensorFlow do it. None of you are ever going to write the solver to do this because it's a done deal. It's a tool that you use. But I will describe it briefly here, at least in principle. at first, trying to find these magic weights seems almost impossible because, say we've got a neuron here. We want to find out how should we set all the weights to the next layer to make it better at recognizing, say, cats and dogs. Let's say this is our network here. We show it pictures and it recognizes cats and dogs and horses or whatever. And we wanted to make it better at recognizing cats and dogs. So we got a neuron way back here. What's its responsibility in this whole process? How can we possibly figure out the right weights to connect it to the next layer, especially considering that then affects all the outputs going downstream from it. So it's unsolvable, right? But let's instead say if we try to bite off one small piece of it with a smaller, tiny network, it doesn't look so insolvable then. Let's say we've got a very simple-minded network with these 3 input pixels to it. It's got this one hidden layer, and it's got these 2 output pixels for dogs or cats. And so we show it this picture, and we get this output. And we know that we're showing it a picture of a dog, so we would like dog to light up, maybe this first pixel, and instead cat is what's lighting up here mostly. And if I say light up, we get floating point numbers out of these networks. So they're going to come out with various values. And in this case here, this one happens to be showing us 0.35 and 0.85. What we'd like to have is it show us, maybe 1 for cat down here and maybe 0 for dog because it's a picture of a cat. But that's not what we're getting. So we want to train this network a little bit better to make it a little bit smarter. We can't do it in one fell swoop, but we at least want to push things in the right direction as we keep showing it new pictures. So with this picture of a cat that we're showing it right now, and it thinks it's a dog, which way should we push things? Well, if we look at just this weight right here, we might guess what we want to do. We want to figure out which way to push this weight to make this a little bit higher and make this a little bit lower. But how much should we push it? Well, that's going to say we want to figure out how much the error, E, depends upon this weight W. And it depends on a lot of other weights too. So we want to only find out the partial dependence of this error on this weight. So it's a partial derivative of the error on the weight, right? Well, for this one link right here, we can actually write that out because remember, we just stepped through the mathematics we have of how it calculates this. We know that it takes the input times this weight and applies this nonlinear function. So we can look for this particular sample. We can work through all the math right here. We can look at the inputs from the previous layer, and we can look at the weights involved and everything else, and we can actually figure out what the derivative is with respect to the weight. This is one of the reasons, by the way, why we like our activation function to have a nice derivative, easy to work with derivative, because it enters into this equation right here. So we can figure out, and for example, in this case here, if we have a sigmoid activation function, we can figure out what the derivative with respect to the weight is for this one weight. That's not anything more than some simple, very simple calculus, right? And we can figure out then, given dE dW, how much we want to push the weight, at least in what direction, and how much we want to push that weight to maybe get this value to come up a little bit and get this one to go down a little bit. So that's not hard to do. But we want to keep extending this backwards so we can get all the way to this neuron right here. How can we do that? Well, again, if we start working backwards, we'll find out that, this layer here, once we tweak this layer, will affect this layer. So we want to see how this layer depends on this one. And we end up with the chain rule basically working backwards with a bunch of partial derivatives, right? And the chain rule from calculus, very straightforward to apply, very mechanical to apply. We end up with a bunch of, chain rule equations here, and hands us a bunch of simultaneous equations for all the different weights to solve. So again, you can see it's not that impossible to think that you could do it for one. It's only when we line it up like this, it looks hard. And back propagation's magic is it says, okay, figure out this one, which way to push it a little bit based on this calculation. And then based on those results, go and figure out which way to push this layer. Then based on that, go and figure out which way to push this layer. That's where the term back propagation comes from. We take our error here, we start propagating backwards the corrections that we want to make to all the weights. So we back propagate, and that's the training phase. That's when we're training what we're doing, this back propagation. And that is a lot more complex in some sense than the inference or learning phase. We got a network that works. We throw some pixels here. We say we just do some matrix multiplies, boom, the answer comes out the end, right? Training is a lot more intensive numerically. We got all these derivatives involved and everything, and we got to work backwards. But you get the idea that we can do it. Well, as we do this process here, we do end up, as I said, at one point, at one step here, you end up with a bunch of adjustments that you want to make to a bunch of weights that depend on each other. So you're handed a bunch of, before I move on to that particulars of solving all of those equations, I'll point out that if you want a more detailed explanation of back propagation, there are some very nice ones out here. So one that I recommend, both of these actually step through it explicitly. You will understand completely what's going on at the end of these essentially half an hour paper presentation. Here's a very good perspective on this from Chris Ulla, who's got a great blog. that explains it. And some of you may know the somewhat renowned explainer of all things mathematics, 3 Blue, 1 Brown. The guy's got a fantastic YouTube channel, and one of his explanations is on back propagation in particular, and I think it's pretty solid. And again, in a half an hour or a little bit more, he will explain every detail of back propagation. So if you want to understand it, you absolutely can. Many of you will just say, it's enough, I understand enough, and TensorFlow does it for me, so I don't care. Now, one of the things that TensorFlow does do for you, but it has to do internally, is it ends up with, from that back propagation algorithm, with a bunch of simultaneous nonlinear equations to solve. And that is not that hard if you've only got a handful of them, but when you have millions or billions even of weights, which we have in these larger networks, which we'll find are quite common, solving all of them simultaneously is a very difficult problem. Fortunately, it's not an unknown problem in that this kind of thing happens all the time. Say if you've got to find an element mesh for, you're somebody that's building, bridges or trying to figure out aerodynamics. Lots of cases in numerical science over the decades where people have had the occasion to solve many thousands, millions, or billions of simultaneous equations like this. And so they developed some great methods, and stochastic gradient descent, or gradient descent in general, is a very, very popular and very powerful one. And gradient descent just basically says, I got a bunch of equations and I'm trying to minimize some function like an error. In our case, we're going to try to minimize the error on our output side, right? We know our error. We want to minimize for each picture of a cat or a dog what that error is. So I want to minimize the error for a bunch of equations I've got. And this is an example right here with 2-dimensional. We've only got 2 weights we're trying to adjust here, and we're trying to minimize some error. So we're trying to drive down, we're trying to find the minimum error here at the bottom of this. However, one of the things we find with these non-convex spaces here, these nonlinear equations give us non-convex spaces, which means we got lots and lots of minimums, lots of local minimums in our space. We'd ideally like to find the global minimum over this big, wavy, large space, but what we're going to have to settle for, because that is impossible, that is asking too much when you've got millions of equations. So instead, what you settle for is you settle for finding a pretty good local minimum. You want to find the best minimum you can that's pretty good. And so finding a good local minimum is what gradient descent's good at. It goes down and down and down, and it finds what's a good local minimum. Now, you might think, hey, but there might be a better minimum over here, and that's where more clever versions of gradient descent will do even more, like, for example, incorporate momentum, which, as the name suggests, the physics suggests, means when it gets to the bottom, it doesn't just stop here and call it a day. It says, maybe I'll investigate a little bit further. Whoops, I found a new place to investigate. So you can tweak gradient descent a little bit to try to have it find a better minimum. Again, you don't try to find the absolute best global one. That's expecting too much. We just hope to find some good local minimum that minimizes our error. And that tells us which way to push all the weights. In this picture right here, it would tell us how to adjust these 2 weights. In general, again, this is happening in many million dimensional space. But gradient descent's good at that. And the tweaks that we find useful in machine learning to it are things like the momentum, changing the step size. How big do you take for each step as you're trying to march your way down this thing? You can take very big steps and get there fast, but then you run the risk of overstepping a minimum. You can take very tiny steps and be sure you're precise, but that's very expensive and you might never get to where you want to get. So step size is the kind of thing. You might make it adaptive even as you go along. So there's some parameters, hyperparameters, yet again, these are actual bona fide hyperparameters in your model that affect how the solver works. So this is how stochastic gradient descent, well, it's how gradient descent works. Now, the stochastic part of the term means that stochastic generally implies there's some random statistical aspect to it. And indeed, that is the case, because what we would do in our simplest, most direct method is we'd show it all the cat and dog pictures and then figure out the best way with this to adjust all of the weights at once. Well, with the very large sample sizes and training sets we find necessary to learn, tens of thousands at the very least, it would take a long time to churn through all those, to accumulate the errors, and then figure out which way to adjust the step. And you could do that. You could go through all the data sets once. That's what's called an epoch. So you can go through an epoch of data, all the data, and figure out which way to tweak the weights, and then go through another epoch and tweak the weights a little bit. But it's been found that in general, it's more efficient if instead we only go through some subset of all the cat and dog pictures. So we maybe only go through 100 of the cat and dog pictures out of our 100,000, and then tweak the weights a little bit, and go through another 100 and then tweak the weights a little bit. We run the risk that we haven't really captured the absolute best characterization of the error, but we're making a lot more rapid adjustments here. And empirically, it turns out that that's almost always what you want to do, is don't wait for a whole epoch. Instead, go with a mini batch, a smaller set of the data, and adjust the weights. and then grab another mini batch. And eventually you'll go through an epoch of the whole data and then repeat that process, generally for multiple epochs. But you want to go through mini batches. The fact that you're grabbing some random mini batches turns this into a stochastic approach. There's some random element to this now. And so that is where this becomes stochastic gradient descent. And this is pretty much the technique used to solve the back propagation equations that we've generated and make neural nets work. Now, again, TensorFlow turns all of this into a one-liner with a black box for us, but you should at least be aware of what the hyperparameters are that we're going to have to select for TensorFlow to use and what they mean. So I hope that higher level view has given you enough detail to choose some sensible hyperparameters, and many people, that's all they need to be effective at using TensorFlow and do deep learning. But again, if you want to understand the precise details, back propagation is explained in its entirety by those two links I gave you. And stochastic gradient descent is a little more detailed numerical method, but it's widely used, and there's millions of resources on that if you really care to know as much as you can about that. It's very easy to grab. You do want to be on GPUs, as I've said, and this is where GPUs become interesting. So you want to be on a GPU slice of bridges, and interact-GPU will get us GPUs instead of just the regular memory nodes we were using previously. You'll want to load the TensorFlow container. There's different ways to load the environments here. I think the simplest one is to use the containers, and the Singularity container for TensorFlow has everything just nice and set up for you. And once you do that, then whenever you start a Python shell up, it'll automatically have the right environment to be able to just import TensorFlow. And now, we're ready to go. There are a couple other ways too you could do this. You can also just run these things directly. You can run them within the shell directly. I've got, for the codes that we're going to look at, all the example codes, they're sitting around in your example, in your big data / CNN network, or mnist. CNN, I think it's big data mnist network folder, excuse me. They're all sitting around right there. So you can find these sample codes of everything we're going to discuss right there, and you can run them very easily if you want to, instead of having to cut and paste them into your shell. But we're going to be working in a regular Python shell. Now, documentation for TensorFlow is wonderful. And again, this is unusual for a lot of this open source stuff because people don't find it a great task to go and contribute to the documentation, and oftentimes the documentation is sketchy and whatnot. That's not all the case for Spark, as we saw previously, and certainly not for TensorFlow. It's another reason I like teaching these technologies. Documentation is fantastic to get off the ground with. So you should probably have, as you do these exercises, you should certainly have open in the browser next to you the TensorFlow documentation. So do that. Now, the problem we're going to start with here is mnist. It's a classic. There's a reason that almost everybody starts with this problem, because it illustrates things very well. It's very tractable. It can be run in nearly real time on modern hardware. It can be trained in real time, so you don't spend a lot of time sitting around between your experiments waiting for it to train, as opposed to more complex problems where today training times are often on the order of weeks to get real research, quality problems to get the training done. So this trains very, very quickly right in front of us. So it's a great problem, but it also illustrates all the important elements that we can build on to much more complex problems after we do this. This problem is going to be character recognition of 28 by 28 grayscale samples. We saw yesterday, we could attack this problem certainly with classic machine learning techniques, and we even did it with clustering yesterday to some degree of success, right, if we used that TSNE approach yesterday. But we're going to find that neural nets have just leapfrogged completely all these classical machine learning approaches for these kind of problems here. So we're going to see how effective it is. So we're going to use TensorFlow, and we're going to recognize these digits. Again, there are a bunch of grayscale images. They are included in TensorFlow. Another reason I like TensorFlow, when we're done, we'll talk about some alternatives to TensorFlow, the main one these days being Torch. And the reason it's kind of 50-50 between TensorFlow and Torch. And the reason I've leaned towards TensorFlow is that it's got a very good ecosystem of tools and everything. That's one reason, distinguishes a little bit. And the Keras interface to it is extremely, extremely friendly. So when I say that, it's important for me maybe to point it out so you don't get confused if you look at older TensorFlow stuff. TensorFlow evolved out of being the powerful production way of doing this. And there were other alternatives like Torch and Caffe that were supposed to be the user-friendlier ways of doing things, but not quite as efficient for production purposes. So they weren't used in industry. Google didn't use them, but they were used in classes. Well, of course, The Google people, or excuse me, the TensorFlow people wanted a friendlier front end interface to make things friendlier. And of course, the Torch people wanted to make their stuff more powerful. So they've kind of both converged to be fairly similar. And when we're done, we'll compare and contrast a little bit. But at the moment, we're using TensorFlow and we're using the Keras API or way of accessing TensorFlow. TensorFlow, to make themselves much more friendly, when they moved to version 2, they took one of the front ends that was very popular, Keras, to make things friendlier to use TensorFlow. And they said, hey, let's just roll this in and make this our default way of using TensorFlow. So Keras has become the first-class API, the standard way of using TensorFlow. So if you look at older TensorFlow codes, and if you look at maybe our old lecture, for example, my lectures from a couple of years ago when we used TensorFlow 1, things were a little bit uglier and less friendly. These days with Keras, we'll find things are very friendly. One of the friendly things they did was they include some data sets right built into it. And we'll look at some of the other data sets they include too, but we're going to use mnist right off the bat. So mnist is built into Keras right there. And all we need to do to load in these images is just do this. Now we've got the mnist images loaded in, and we'll see what they are. They're a bunch of images, each one of which has a label attached saying what the digit is, because we're going to train the network. So we need to show it a picture of a 9, and we need to tell it this is a 9. So that's the, that this is the image and its label. And this is what we need to do supervised learning. In other words, we're supervising it, we're telling it what it's looking at. And so we're going to have a bunch of these loaded in, and we're also going to have a set of test data loaded in. As we know from our earlier discussions, it's very important when you think you're doing the right thing in machine learning to be able to verify it somehow with test data. And we're going to find a number of hyperparameters here that we want to adjust. We've already mentioned a bunch of them, and we'll find ourselves having to select them now as we write the code. And we need to have some way of verifying that we're not overfitting our problem again. And our test images will allow us to do that. So mnist already breaks them out for us. It's very nice like that. So when we load mnist, we're going to get some training images and some test images, and we're going to work with them. Now, if you think there's anything mysterious or complex about the format of these images, I assure you they're extremely simple. So I give you as some sidebars here. I don't want to stick them in the code, embed them in the code and muddy the problem up, but I have some sidebars as we go through here of some simple matplotlib code you can use if you want to, verify what we're looking at. And you can see that if you take any one of these digits and you look at the actual data here, it's nothing more than a grayscale image, 0 to 55 integer grayscale image. And you can plot 28 by 28, and you can plot it out like this, and boom, you can see how simple it is. That's all it is. The digit 4, it's got a label 4, and it looks like a 4. So again, at any point in time when you're playing with this stuff, you can pull it out and dissect it and pull it up. Again, don't try to run the stuff on bridges unless you've set up a remote viewer with X Windows or something. Save this pretty much for your laptop experiments. But I also don't want to stick them all in the code and confuse things. But it's that simple. So here we go. We've got our test images. We're going to load them in, our training images. And our images, as I've said, are 28 by 28. But I also told you our networks, right, are just a bunch, our input layer is just a big one-dimensional vector. It's a bunch of neurons in one dimension that we've got to throw the image at, which means we need to take and effectively stretch out this image into a one-dimensional vector. It actually represents 784 dimensions, right? They're the bases of a 784 dimensional input into our network. So we're stretching out our image, which comes in as a 28 by 28 image, into one 784 long vector to throw at our matrix. And you might object to that right away and say, you're losing a lot of information here about the relationship of pixels and everything. Nah, that's a fair objection. We'll see later on how we might not throw that information out. But at the moment, we don't have any alternative, right? How can I throw a two-dimensional image at my one-dimensional input layer of my neurons? And the answer is I can't. So I'm going to stretch the thing out into one-dimensional 784 long vector and throw it at, so we can later on throw it at our network. And I do the same thing with our test images, convert them to floating point numbers, because you don't have to. You could actually try to train this with integers and it will work, but it's, for a variety of reasons, it's maybe more efficient if we scale our floating point numbers to be close to kind of 0 to 1. Maybe that works better with our activation function and the range of our floating point numbers, et cetera, et cetera. So you'll find that's often an effective thing to do, is to try to constrain your results to be floating point numbers that are 0 to 1-ish. Not absolutely a requirement, but we're going to do it because it's a good practice and it will perform better. Okay. Now it's time to build our network. So we've got our, our data basically set up to feed into a network. Now we have to tell TensorFlow how to build a network. And this is where the Keras interface is incredibly friendly and simple. It is as simple as just feeding it a bunch of layers on whatever kind of network we want. And I'll go through this in detail, but basically we just decided that we want a network that's 64 and 64 neurons, and that in the layers. That's how big we're going to pick it. And these are hyperparameters. Why did I decide I want that many neurons? Because that's what I feel like at the moment. Maybe I think that's powerful enough to do it, but small enough that it'll train quickly. Maybe I'm guessing. Maybe I saw somebody else online that did an mnist with this size network. At any rate, this is a hyperparameter, and you've got to pick one from somewhere. Again, your best precedent, is the best way to go. And so we're picking 64 by 64. We'll see if it works. And if it doesn't, we might have to adjust our case. We are going to try different experiments here. We're going to play around with different sizes, but this is going to be our starting point. Now, the input to this layer, how many neurons we have on the input layer, is not up to us. That's determined by the problem. We have 784 pixels from our images, so we must have 784 neurons on the input side. That's not up to us. That's not a hyperparameter for us to choose. Likewise, on the output side, on our last layer, we have 10 outputs. That's not up to us either, because we have 10 digits. We want each neuron to represent one of the digits to light up with a probability for that digit. So we don't get a choice there. We got 10 on the output and 784 on the input, but we do get to pick for our two layers here how many neurons we have, how smart we want it to be. And I've picked two layers of 64 and 64 neurons. I could pick more layers, we will later on. I could pick wider layers, we will later on, but I'm going to start out with this as my best guess as a workable network. 264 neuron layers. And again, the input's determined by the problem, the data set for us, and the output's determined by the kind of outputs that we want, the classification. So here's the entire network. You can see how easy it is to define and to change and to play around with in TensorFlow. So, and again, this is the reason the Keras interface is so user-friendly. Now, we have to initialize these neurons to something. We can't start out with all zeros for a couple of reasons. One of which is, our back propagation algorithm needs something to start figuring out which way to push weights, and a bunch of zeros won't allow it to bootstrap. Another thing is we don't want, say we initialize them all to say 1. We said that's our random value. We just set them all equal to 1. That would be bad, because each one of the neurons is going to look exactly symmetrical to the others. So they're going to push the weights in the same direction. And neurons aren't going to learn anything different from each other. We want the neurons to start to learn different things, right? And so if we set them all equal to 1, they'd all track each other. They'd all do the exact same thing, and that's no good. So instead, we want some random numbers to initialize them with. Now, what values of random numbers? Should they be from 0 to 1? Should they be from 0 to 100? Should they be from -2 to +2? This is an open question. Again, it's one of those things that the best you can do is take a guess as to what other people seem to be having some success with. And the answer is you want to pick some reasonable values, which turn out to be some standard deviation. It gives us between -1 and 1 kind of things, or 0 and 1 is what people often use. And so the defaults here for us are going to work just fine. But we also have the ability to actually, TensorFlow is happy for you to give it suggestions as to various other distributions. You can pick standard deviations and medians for other distributions that you want. But we're going to go with the defaults. But it is an open question, and it is also another case where some randomness is coming into our solution yet again, right? I keep saying, wow, it's amazing how we want to do these deterministic learning problems and we keep having randomness. Well, we need some random values to start our neurons out with. So this is where we've got some randomness. So, and again, we can, if we want, we can control the seed, we can control the distributions. We're going to go with the defaults here. Keras, one of the things Keras did, that original TensorFlow was a little more explicit about all these. The Keras one is like, we're happy to let people just go with our defaults. So Keras by default, we don't have to enter in values, but we certainly can. Okay, so we've defined our network completely. This actually defines the network in its entirety, tells it everything it needs to do. By the way, here, our activation function also, we're explaining what to do. This last layer activation function I haven't explained yet, I'm about to, but these two activation functions on the first two layers, the ones that really count, are rectified linear, right? That's as I said, the most common one these days, and we're going to find it works just great for us. So we can define lots of details on these layers, some other details too, but we're going to go with this. So this is pretty much a default layer. Okay, now we decide it's time to actually say, tell this thing to start solving our network and and finding the right weights. Well, in order to do that, it needs to know what the error is for this. What's the error for each one of these things? How do we define error when we showed a picture of a cat and it sees a dog. We kind of said what the error was for 1 pixel if we want it to be 1 and 0, but in reality, it's going to say for digits, or we can talk about digits since that's what we're working with. In reality, for digits, it's going to give us a bunch of probabilities for each digit. How far do we say that that is off of our correct answer? And we would find that we have a number of options available to us for error, as always. We could use something like some mean squared difference or something, but instead, what we're going to use is sparse categorical cross entropy. And I'll explain exactly what that is in a minute. But first, I'll point out that once you've built your network, Tensorflow, one of the things you can easily do is pull up the model summary for it. And the model summary will show you exactly how many weights you have for each layer. And we can see what's going on here. You can see how these weights add up very quickly. I mentioned to you earlier that network can have billions of weights these days or more. And here's what we've got. We've got in our first dense layer. So dense is by default our normal neural network layer that we're working with, a fully connected or a dense layer here. All the neurons are connected to all the other neurons, which is the default. We'll look at some alternatives, but this is the default. And that layer is going to have 50,000 plus parameters, right? That's going to be basically 784 times 64. That's how many parameters we've got, weights we've got connecting the input layer to that first 64 layer, right? That's just this matrix. That's how big the matrix has to be. The next layer between the 64 and the 64 is going to be roughly 64 by 64, and that connects that up. But not exactly. We'd also notice there's some bias layer. There's some biases in here too. So if you want to get the exact number, you'll notice each layer has a bias in it for each of the neurons. So we have some biases in here, and we have the weights. And the last layer is going to be the connection between the 10 outputs and the 64 neurons in the preceding layer. And so it has 640 plus the 10 biases. So this is all of our weights right here. And we end up with 55,000 plus parameters, even for this tiny little network here. So again, you can see how the parameters add up quickly. So let's talk about that last layer, that softmax layer, because it's going to be very useful to us on several levels, one of which is normalizing the outputs, which somebody always asked about, because it would be nice if our outputs reflected the nice probabilities of the guesses. By default, the output, the result of all of our matrix multiply nonlinear function math are going to be a bunch of numbers that range between negative large values and positive large values. But you might like those to actually, it's nice if they reflect some nice controlled probability. So the real outputs coming out of our network might be, let's say we have a 3-digit network. So if we have 3 digits, the numbers coming out might be 4.8. That's probably our best guess. It's the largest positive value. Negative 2.6. That's probably saying I'm very unlikely this is a 1. And 2.9. It might be a 2. So this is the kind of raw outputs that you might get going into the output layer. But then the output, but again, we'd like this. So what's a good way to kind of get from here to here? Well, one thing we can do is you can just apply an exponential function to the data. And that's going to stretch our results around. It's going to make our biggest result much bigger. It's going to make intermediate results not quite scale as large. And it's going to make negative results tend towards 0. So that's a nice characteristic. So if we just exponentiate our values, we stretch things out. And that's good. But now let's just stuff all those back down so that they add up to 1. So now all we need to do is divide by the total here to normalize these back down to 1. And boom, we've got some nice normalized values where rounded off, this is now 87% probability it's a 0, 13% probability it's a 2, and 0% probability it's a 1. So softmax is just a very straightforward function that does a nice job of scaling our outputs to probabilities. So that's what we're going to use for our output. Now the error that we get from that, so we've got our output values, but what about the error that we need to tell the solver to use to say how good am I with these weights? How much do I need to push these weights? Well, it turns out for categorization problems like this, a very popular error is the cross entropy loss. Again, there are different errors that could work. We could do something as simple as some kind of root mean square error. There's lots of choices, but cross entropy is one that's very favorable for this category of problems, and it's very simple too. One way you can think of it is by using a logarithmic function on the data, it kind of undoes the softmax. That's one way to think of it. So it kind of accounts for softmax. Another way to think of it, well, the term entropy here scares a lot of people. Entropy is an incredibly over-abused term. As a physicist, I find it ridiculous how just anything that has the same formula as entropy from thermodynamics somehow grabs the term entropy, even where it doesn't apply in any intuitive sense. Information theory has done a good job of that. And so cross entropy here is basically, on one hand, like I say, it's undoing the exponential function up here. And on the other hand, it's pretty good at matching up categories when you know that only one is the answer. So what it does is we're just simply saying that I'm going to take the fact that this is the correct answer. I know when I'm training this, and it's also guessed the largest probability. So it's going to have a very small contribution to the error. If it guessed the wrong one here, then the contribution to the error would be much larger. So this is just a nice formula that gives you, penalizes greatly bad guesses and doesn't penalize greatly a bad guess if it's got a low probability. So that's all this cross entropy loss is. So it's a nice simple error. It's not complicated or difficult to understand what it's doing. And that's what we're going to use. Yeah, it's very popular with these kind of problems. So what we did was we completely, get this box out of the way. What we did here was we completely defined now everything that TensorFlow needs to know in order to know what the network looks like and how to solve it. It says, okay, this is the error, or it's called loss here. Again, you hear error, loss, cost. These are all synonyms you'll hear in machine learning. So our loss here is going to be the sparse categorical cross entropy loss. It's this predefined function, but it's just simply the one we just looked at. And so that tells it the loss. The solver that we're going to use, it could be generic stochastic gradient descent. We'll try that later on just because we can. But instead, I'm going to get a little fancier here. We're going to use a variation of stochastic gradient descent that has momentum. I like that momentum stuff. It turns out to be effective. And also one that's got an adaptive time step. And so our adaptive time step momentum one is atom, adaptive time step momentum. So our atom solver is just a variation of stochastic gradient descent again, and it's one we're going to use. We can plug in different optimizers very easily here, so you can see how trivial it is. So at this point, we've now got TensorFlow ready to go. It knows what our network looks like. It's got our input data set up, and we've told it what kind of error we want to minimize and the exact optimizer we want to use to minimize that error. So we can now go ahead and we can tell it to run. Oh, and we're going to tell it also this metrics accuracies because we want to, as you solve this, why don't you keep track of us for us? Keep the accuracy as you do each one of these time sets. Let us know what the error looks like so we can track the error as it gets better and better. That'll be nice to see. So we're going to run this thing here now, and so we'll collect the history as we run it so we can plot it afterwards. And this says, okay, go ahead and run this. Here's the input data that we want you to use when you run this, the training images and the training labels. So these are the grayscale images. These are the labels for each one of them. We're going to tell it that the batch size is, because we want it to go over all 60,000 images here, and it's also test images too. We're going to go over 60,000 images. We're going to do 128 at a time before we go ahead and update the weights with the solver. And we're going to do that for 40 times for the entire data set. So we've got 40 epochs here, and we're going to go through each epoch with a byte of 128 samples at a time. And we'll tell it to be verbose, let us know what's going on here while it does this. And here's some validation data that you can use. So after you do every one of these adjustments and you've minimized the error, you can go ahead and test it and see how well you're really doing with these, which haven't been used to train it. So at least these aren't going into overfitting the training data. They're not used to test the images here. They can just report the error to us. So this is a nice, very simple way to specify everything we need to know to go ahead and tell it to run. And when it runs, these are the kind of results that we'll see spit out. It's going through all 40 epochs here. I've kind of cut out the middle ones here. And each time it runs, it's going to tell us how long it takes for each sample, and it's going to report the loss. And the really thing we care about is not just the accuracy on the training data. We'll see that it gets very good. We can see this overfitting in action here. Every one of the things we're going to do gets very good at fitting the data, at recognizing the digits that it's training on. So its accuracy here is perfect. However, how well is it really doing? How well is it generalizing to our test data, right? That's the way we should phrase it. Well, we can see that when it reports the accuracy on the validation data, which isn't being used to adjust the weights. And we can see it's really only 97% accurate. Well, 97 is not terrible, but it's certainly not 100%, which it basically is. So we can see this thing in 40 epochs gets very good and fits the data, the training data perfectly. But some of that isn't really turning out to be so useful here. It might even be some overfitting, which we can see if we graph this out. Now, if you want to actually graph this stuff out, here's a way you can do it with matplotlib. This is what I did for the graphs that we're going to look at here. Very simple little just piece of code. And we can look at the results like this. So we can see the model loss, or inversely the accuracy. So this is just the inverse of this. We'll just look at accuracy from here on out, but loss is the same thing. So if we look at the accuracy from here on out, we can see that indeed our training data, it learns pretty quickly and gets up to here to very nearly 100% accuracy on the training data. However, our test data, does not do quite so well. It gets up here and it gets stuck. So even though the training data keeps improving, we're not getting any better here. We're wasting our time after the first 10 epochs or so. We're stuck here, 97%. So there's no point in going past here. This is all just pure overfitting in here. This is just wasting our time and fooling ourselves. So this is overfitting in action again. We think we're doing better and better fitting the data, but we're just memorizing the digits instead of learning what they really look like. That's another way you can think of it, is overfitting is where machine learning algorithms can get good at memorizing. Hey, the third sample is a 4. I'm not even looking at it. I just know the third sample is a 4 because I saw it before. Whereas you really want the network to learn what a 4 looks like in general. So instead of memorizing things and overfitting, we want it to learn. And we can see we quit learning here after about 10 or so epochs. So that's how well our network did. But again, 97% might be pretty good. Usually this is a point where somebody notices, as a matter of fact, that, hey, how come for a moment there the test accuracy was actually even better than the training accuracy? That's strictly an artifact of the fact that for the first batch, things are a little bit out of sync and that you test at the end of the batch. So the test has the benefit of a whole epoch of training, whereas the training data is reported earlier where it's not there. So that's not a phenomenon that's really interesting. It's just strictly a matter of your reporting later on. And also regularization techniques, which we'll look at later on, are only turned on for the training data, and that makes the training data skew a little bit. So don't worry too much about this phenomenon. It's not something interesting going on. It's just, like I said, it's an artifact of the way that we're reporting the training and where it's actually reported. Once we get into the interesting part of the curve, that doesn't matter. So, we got to 97% here. That's not terrible. We're recognizing digits pretty reliably, but can we do better? Well, with TensorFlow, it's very easy to find out. Let's just go with a wider network. How about that? Let's give it a shot because it's easy to do. So now we're going to go with 512 neurons wide in both of our layers. Just change a couple values, run again, and here's the results that we get. And we can see that we're now up to 98.2 accuracy. So we definitely improve things by going a little bit wider. And we can see our graph here. We're still overfitting. We're still, we haven't solved the overfitting problem, but we did better. We at least got up to 98% here with our results. At the expense, though, of we've got a lot more parameters. Our total parameters here are up to 600,000 now. So our problem's growing rapidly as we get more aggressive with the size of our network versus 55,000. So we're 10 times more parameters. But hey, we're getting better results. And this is still relatively small and relatively fast to train. So we're doing pretty well. Okay, well, if that was good, how about a little bit deeper? And again, those of you who are expecting me to now give a very analytical explanation of why we're going deeper, well, I hope by now you've given up. You should give up. We're going to do some hand waving. We're just going to try it because we know deeper gives us some more flexibility, more powerful functions, blah, blah, blah. But in general, we just know that deeper equals smarter. So we're going to try that. We'll see what the trade-offs are with deeper. One of which is it's just going to take longer to train and because we've got more weights. And so that's more painful. Another one of which is we're going to find out that deeper networks run into the risk of having vanishing gradients, of being harder to train. And we'll talk about that. So just going deeper by default is, at the very least, a disincentive is it's more expensive, but we're going to try it because let's just go deeper. So it's trivial to do that in TensorFlow. So let's go deeper. And here's our 3-layer network. A lot more parameters right now, but hey, our accuracy is, up to worse, 98%. We just lost some accuracy going deeper. So as I said, it not only took longer to train. If you go up here and look at this data, time-wise, it took us a lot longer to get here. So when you run these experiments and you're sitting there waiting for it, you'll notice that. It took you longer to train this, but it got worse. How did that happen? And this is the vanishing gradients. If we think back to our solver, and we didn't go deeply into detail, but we went into enough of our backpropagation algorithm to where you saw we had those partial derivatives, dE, dW, right? We needed to know how things are changing to know which way to push our weights. Those gradients are a big part of our backpropagation algorithm, the gradients derivatives, right? That's a big part of how we adjust our weights. Well, you can imagine as you stretch your networks out that there's a tendency for the gradients to become shallower from one layer to the next. And that makes it harder to push things in the right direction. And indeed, with deep networks, the vanishing gradient problem is the foremost problem. And to the extent where 20 years ago, people thought that was probably the most limiting, the biggest limitation on neural nets is that we just can't make neural nets deep enough to be smart enough to do useful stuff. So 20 years ago, if you said to people, what are one of the impediments to neural nets being useful, and because back then, again, they were that niche, exotic area of machine learning, people would have said, well, vanishing gradients, you just can't make networks deep enough to have the smarts to do interesting problems. So too bad, we can't use them. Well, we can see that effect here. By us just making the networks deeper, we're not just magically gaining smarts, we're paying a penalty, not only in the training, but we're just not gaining, it didn't get smarter. So vanishing gradients are a big problem. We'll see some ways to address that, but it means we can't just overpower this problem. But instead of just dealing with vanishing gradients, we're going to instead go off in a different direction and use the number one tool for lots and lots of spatially and temporally dependent problems, which is a convolutional layer, a slightly different layer than our fully connected layer, a different architecture, which is incredibly powerful. And it is going to give us a huge leap up in terms of performance. It was revolutionary when people started to apply these things so effectively to these image recognition problems. So let's look now at a different approach and a very, very powerful technique, widely used for a wide class of deep learning problems, which is to bring convolutions into it. And so this image in front of us is pretty much a big breakthrough at least it exposed the world to how powerful this technique was. It didn't pioneer the technique. It did pioneer a few of the smaller techniques used within it, but it really broke open image recognition. And that is AlexNet, which took, so far we've been using mnist, the standard character set. I should point out the history of mnist is back in the 90s when people said we're doing digit recognition, which was state of the art back then, right? The Postal Service for recognizing zip codes or whatever, it was state of the art, was image recognition, these simple characters back in the 90s. And people said, let's have a standardized character set so that we all are working on the same problem. And so some poor, probably graduate students somewhere had to go and label a bunch of these grayscale images and maybe even write them and come up with a data set. So data sets, human labeled data sets are painful and expensive. It's one of the reasons data is so valuable and people want to keep recycling it and not set aside test data and everything. But at any rate, mnist became a standardized data set. And that's a very powerful and effective way to make progress in the field. And it established this precedent in machine learning to where there are standardized data sets that everybody works on, and it can give us a comparative idea of what the progress is and which techniques work well. And ImageNet, around the 2010s was the standard data set that people were intensely working on to do image recognition. And it is, we'll look at it and we'll solve some of these problems. It is 100 different categories of images. There are higher resolution color images. And it was the competitive problem everybody was attacking. And people were still using a lot of different machine learning techniques, not just neural nets. And AlexNet came along, and with neural nets and with this particular variation on neural nets with convolutions we're about to look at, blew everybody away. It leapfrogged previous progress, made a big quantum jump in progress in accuracy. And so it got a lot of attention. And ever since then, people have just said, of course, convolutional neural nets is the way to do every single imaging problem or anything that looks like imaging. And so we're going to use these convolutional layers here for our imaging problem and find out how they apply to many, many other problems as well. This is what AlexNet actually looked like. And we're going to step through all these layers and see what these mean. This is just an overview before we dive into this. But first of all, it's important to understand what a convolution is. So a convolution is this idea of dragging some filters over an input image. And our input image here is just 4 by 4 pixels. So picture this though, for our real images we're going to work with, this will be 1,000 by 1,000, but we've got 4 by 4 for this illustration. And we're going to drag this filter over our image to give us this new transform image. And we might have different filters looking for different things, so we might end up with different outputs. So this is the math though of a particular convolution. It's very, very simple. Again, it's these add multiply kind of ideas here, is that we take this filter here and we multiply, so if we're trying to generate this new pixel here, this filter centered around it, and we take I1 times A1, so the data times the filter value, and we come up with a new value to add to I2 times A3. And we keep adding all of these together, and we do these 9 additions, and we end up with a new value here to stick into 06. So that's what a convolution does. Now, there's some, you might worry about the indexing and on the edges, what happens, there's padding and whatnot when you hit a very edge. And we just do some simple, obvious things in general. You have options, but in general, people prefer this simple-minded thing. Let's just pad it out with zeros, and that's how we get to the corners. So no big deal there. It's just a detail. But here's what convolution can do. They're very powerful. So here's a classical edge detector convolution, which people would use way back in the 80s and 90s. If you bought a digital camera back in the 90s, this is the kind of image processing that it could do internally. Here's an edge detector, applied to an image. So if we have an image like this, and we drag this convolution over it, we would end up with this kind of output. And you can see why it's called an edge detector. Kind of does a reasonable good job of picking up the edges. And it's kind of amazing that this simple-minded math operation can detect edges so well, and yet it does. So that's the power of convolutions. Now, for many years, convolutions, handmade convolutions like this were interesting to people that did, digital photography or signal processing of various sorts, and they handmade these convolutions. We're going to find instead that our neural net will learn convolutions that it can use to find edges and combinations of geometrical shapes. So they can take and look at a picture of a cat, and it can figure out that's a cat by finding maybe the edges of the cat first, and then assembling those edges into outlines, and then assembling some of those to say this is an ear, and it might have a filter that's good at finding ears and eyes, and eventually it can build it all up and say, hey, that looks like a cat by applying these convolutions. And by the way, this goes back to the biological inspiration. A lot of people do believe that the human visual system, and not just believe, there's experimental evidence to strongly suggest the human vision system works by that. Your retina, things start to build up edges and whatnot. So by the time things are deep in your visual cortex, a lot of that pre-processing has been done. And so your visual system is building up things with these kind of operations. But at any rate, the classical digital convolution technique is used in deep learning instead, where we learn these convolutions as we go along. So here's the kind of thing that happens. So here's a real image with more pixels, still not very high resolution, but it's a little bit better representation. And we can apply these convolutions across all these pixels here so that we can detect, let's say, edges, just at the very least. So at the very least, before we go into our fully connected layers, that's what F stands for here, our regular or dense layer, the normal neural net layers that we've talked about so far. So before we feed our information into our normal layer, we've already picked up a lot of useful information. It's learned a whole lot. And more importantly, it's also retained geometrical information. And convolutions are applied to a two-dimensional image, right? We had to stretch our image out and lose all of that, relationship between pixels to do our normal network. Now, these convolutions are good at working with two-dimensional stuff, or higher dimensions in some cases, but particularly in two-dimensional cases. They're good at detecting stuff, so they can find edges and nice information across the space of our image. And so by the time we get into the deeper layers, a fully connected layer, we've picked up a lot of useful geometrical information that it can start to assemble. It doesn't have to do nearly as much thinking to figure out what it's looking at, whether it's a digit or a cat or a dog or a pedestrian. It has a lot of information. And as a matter of fact, this concept is so good and so useful, why don't we stack them? So that one convolution layer, the first one that figures out edges, can feed into the next layer that can take edges and assemble maybe shapes. And then we can have another layer that takes those shapes and starts to figure out noses and eyes or whatever if it's looking at cats. So these convolutional layers can get smarter as they go along. They can go from looking at low-level stuff, usually called style at the lowest levels, to higher level stuff called content, which assembles into useful stuff. Or another way you can think of it is we're zooming out on the image from the details to the higher level perspective. And the convolutions can do all this work so that when we finally get to the really smart thinking layer, which has a lot more, which is more expensive to train, it's got more weights for these fully connected layers and everything else, but it has a lot of high level perspective on what it's looking at. So this is the magic of convolutions. And let's look at this in a little bit more realistic of an operational scheme here, where we've got an input image here, again, kind of low res, but fits on the screen well. So we've got an input image here, and we're going to scan a number of kernels being the term for filters here. We're going to scan a number of filters across this image. We're going to decide, here's our input layers. We've got 3 of them. Maybe we got 3 because we're coming from some previous filters, or maybe we've got 3 because this is the RGB channels of a color image. But for whatever reason, we've got 3 different layers coming in from the previous image. And we're going to apply a number of filters to those. We're going to choose, again, these are hyperparameters. We're designing a network we get to choose and play with. I'm going to choose to apply 2 filters to our 3 input images. So these are our 2 filters called W0 and W1, which means each one of those filters has to have this many weights because it's reading in from 3 layers. So each one is going to be 3 by 3. We can also choose the width of these filters. So far, we've chosen, I think all of our examples are 3 by 3, but they can be different sizes. We're going to have 2 filters, each one of which is going to be size 3 by 3 that have to be given on the input side. They don't have a choice. They're given 3 input layers. And that means because there's 2 filters, they're going to be 2 output layers. So this might be RGB channels coming in, for example. Maybe in the output layers, these filters are learning to recognize edges. Maybe this one recognizes vertical edges, and this one recognizes horizontal edges, for example. So that's the kind of setup we might have here. Let's look at the mechanics of how this works as we scan over the image. So at first, the filters scan over one chunk of the image, then they move over and scan over another chunk of the image as they're generating this pixel down here. So this is where filter 1, which has this output layer, is generating this value 8 by doing all these add multiply operations, right? They're very simple operations, right? It's just going and saying, okay, 1 times 0 plus 0 times 0, right? It does that for all 9 of these elements and all 9 of these elements and all 9 of these elements, and ends up with 27 numbers to add together. It ends up with the value 8 right here. So likewise, it scans over a little bit further, and it does these 27 add multiplies and ends up with this value of 3. So the math is very simple. And conceptually, we're just scanning over the image like this. And we're coming up with new values for the output layers. And depending on what these kernels are learning here, these output layers, like I said, this might be vertical edges, this might be horizontal edges. So I hope you can understand the mechanics of this is very simple and straightforward. It's only when we build them up into layers and everything that powerful, magical stuff starts to happen. Okay, now I am getting the Zoom internet connections unstable message, which is always frightening. So please alert me if indeed I become unintelligible. I hope not. Okay, so this is convolutional layer here. And let's see, I have no feedback from everybody. So I really hope I'm not entirely cut off from everybody. So even
audio's good, John.
Oh, okay. Glad to hear that. I have my Zoom internet connection unstable warning right in front of me still. Okay, so the convolutions are very straightforward. Here's the detailed math that gives you how many weights we really have going on and everything. And again, it's what we just looked at, but it shows you how many hyperparameters we have. So let me mention them explicitly. First of all, we have the number of filters on each layer. That's up to us. How many different features or characteristics do we want the filters to be looking for? How big should the filters be? They could be 3 by 3, like our previous example, or 4 by 4, or 11 by 11. We'll look at an example. Another thing that you may or may not have noticed in a previous example was how far it's skipping on each one. The previous example, we didn't skip 1 pixel at a time. We were actually skipping 2 pixels at a time. So that's called the stride. How far do you want the filters to skip? If they're big filters, maybe they can go move in big chunks. They could move 1 pixel at a time, but if it's a 10 by 10 filter, you could also decide to move it maybe 10 pixels at a time. Look at 1 chunk at a time. So that stride is important. And the padding on the edges is kind of a trivial thing, but it does figure into the math. So, we have a lot going on here and a lot of hyperparameters to choose to make our networks work well. At the end of the day, our convolutions could, stacked one on top of another, filter our images down and funnel everything down from the low-level content to the high-level content to feed into our fully connected filter. But we are going to find that this notion of filtering our images down to get from the low level to the high level perspective is such a useful thing to do that we might want to zoom out even faster. We might want to, between one convolutional layer and the next, even do a zoom out. And if you think about zooming out on a picture, you can do that simply with Photoshop. If you're in Photoshop and you take an image and you shrink it down, right, that's giving you kind of the zoomed out view of that image. And so we might just manually want to zoom out to get from the detailed stuff to get to the higher level perspective. So our convolutional filters can figure out in the low level detail, they can get the lines and the edges, but then we want to zoom out faster so they can start to figure out where the heads and the arms and the hands are located in the picture. And so that zoom out can be done with pooling. And pooling is, well, basically, zooming out. Pooling has a couple of different ways we could do it. Now, if you just think of the Photoshop analogy, you might think when you zoom out on a picture, the obvious thing to do when you zoom out is to take and average the pixels together, or maybe even get fancier, use like a bicubic filter or something. You want to take, and if we're going to zoom out by a factor of 2, we want to take those 4 pixels and average them together, right, to get the new average value. And indeed, one way you can pull out is averaging pooling, and it's something that's available to you in Tensorflow. But it turns out that experience shows that a different simpler sounding and cruder sounding way of pooling called max pooling works even better in a lot of cases. And max pooling is just where you take, of the 4 pixels, maybe if you're pulling out by a factor of 2, of the 4 pixels, just take the maximum one. And so max pooling just picks the maximum value and passes it along to the next convolutional layer. Now, again, that sounds cruder, but it turns out it can be more effective in a lot of cases, and it's probably the most common type of pooling that people do now. One reason it seems to be most effective is it picks the most interesting feature, right? Your convolutions are finding stuff. Well, max pooling is going to pick the pixel that's highlighted the most, maybe that's got the most interesting feature. So that maybe is one reason. Computationally, it might be cheaper, and that's worth something in the end. It allows you to be more powerful elsewhere in your network. It is a more explicitly nonlinear function when you're doing actually a max operation. And nonlinear capabilities, we see nonlinear stuff gives us some different capabilities in the way we're transforming our data. So at any rate, max pooling is the one we're going to use here in our next approach to this problem. And it is a very common one as we go between one convolutional layer and the next, and then eventually pass all of this high level information onto our fully connected layer. Let's look at AlexNet here again. Like I said, it's a groundbreaking example, and it used pooling very effectively. It used aggressively, it used a rectified linear function. It was probably really the most encouraging promotion of that at that point in time to people adopting rectified linear instead of smoother functions they used previously. And so it does a bunch of these things we just talked about right here. We can look at the diagram in detail now, and I hope you can at least see step by step what it's doing. We can see, like, for example, the input image here, which was 224 by 224 pixels for these ImageNet images. It used 11 by 11 kernels, filters, on the input images it scanned over with. And how many of it had? It had 96 of them on the first layer. 96 of these 11 by 11 things it scanned over the first layer. And then you can see as it passed along the succeeding layers, what size and how many different kernels there were. And eventually, at the end of all these convolutional layers, it passed it on to a couple of 2048 by 2040 neuron fully connected layers. And those fully connected layers assembled all the information finally into the 1,000 different categories of objects it could be looking at on the output side. So I hope now you can see each one of the steps in this schematic here and say, okay, I get what it's doing. I could even mathematically with a pencil go through and number crunch all the things that it's doing if I had to at a low level. But here is the more important thing to absorb from this, is that the filters that it learned on this first layer alone right here, and we can see the filters that it learned, here's the values for the filters, none of them are as simple as edge detector or eyeball detector. Instead, they are these abstract things that the network learned how to identify. And that is mysterious. It's a black box kind of behavior, makes people uncomfortable, but it is the reality of neural net machine learning, is that it is that the machine has learned these mysterious insights that it can assemble into a final result, but we can't turn them into human readable terms explicitly. This is very similar to the recommender system we looked at earlier today, where I said the algorithm is learning these latent effects, and we can control how many latent effects are available to it, just like we control the number of filters here. But the latent effects, I said, in the recommender system were not as simple as director, actor, genre. Instead, the latent effects were mysterious internal representations, right? Here, it's the same thing. These are the filters. And if you take and run one of these filters over the image, you might well guess that it seems to be doing some kind of edge detection, or this one finds bright spots or dark spots, but it's not going to be as simple and clear as some hand-constructed filter. And that's the reality of these filters. Now, let's try and apply this technique. We're going to find out that TensorFlow makes it very easy to do. So here's TensorFlow. Now we've converted this into using convolutional networks. And there are a couple of significant differences here. The first one of which is we're no longer smooshing out these images into one-dimensional vectors. We can leave them in their natural representation as 28 by 28 images. And that's, again, my early objection was, wow, aren't we throwing out information? Yes, we were. And we're going to find out how much more effective we can be when we don't do that. So the convolutions can take 2D inputs. Matter of fact, they require them. And so that's what we're going to do here. So we're not going to smush this out into a 784 long vector. The second modification we're going to do here is very easy to do, which is we're just going to say, hey, let's make our first layer a convolutional 2D layer. Now we have some hyperparameters we have to pick here, namely how many kernels, how many filters do we want to have in that layer? And we're going to pick 32 of them. Why? Well, because I feel like it. Somebody told me that might work well with mnist. Maybe I saw that with another mnist problem. Maybe it's just a guess and I hope it works. But at any rate, like hyperparameters, the best you can do is find a problem that seems to be similar to yours and use that as a starting point. How about the size of the filters? Well, my guess is that 3 by 3 might be good enough for these relatively small images. So I'm going to guess 3 by 3. And again, that's my best guess. Our activation function, once again, will be rectified linear. And the input shape that we have no choice, right? This is the problem. So the input layer shape is dictated to us by the problems, 28 by 28 images. Okay, then before we go on to the next layer, we're going to do some pooling. As I said, pooling is a nice way to zoom out on our images very quickly and get some higher level detail. And our images aren't particularly big here, but it's going to be useful and effective nonetheless. So we're going to pull these things out. We're going to have one layer here, and then we're going to pull out, zoom things out by 2 by 2, pulling. So basically zooming out by a factor of 4, well, factor of 2, zoom out, and combine 4 pixels into 1. And then we decided that's it. We're going to see if one convolutional layer, because I've hyped this technique so much, I said how powerful it is. Is that enough to now feed into a fully connected layer? Is one convolutional layer going to do it? Let's find out. So before we feed this back into the dense layer, though, we do need to flatten this out because, as we said, a normal dense or fully connected neural net layer wants an input vector. It needs a one-dimensional input vector. And so we need to flatten things out. And so we can easily do that in Keras. We can just say flatten this out. And so pass that then into a 100 neuron smart layer. And this 100, it's a number I picked. I decided I think 100 neurons might be smart enough to make this work. And that's what I did. So I'm going to take and flatten this out into a 100 neuron layer. And then our last layer isn't really up to us to pick. It has to be 10 because we have 10 digits for our output layer. And once again, we're going to use that softmax output layer to normalize our results. So here's our network. Let's see how well this works. We're going to do kind of the same things we did before, only, hey, while we're being all experimental here, why don't I try a slightly different one? I'm going to go with this stochastic gradient descent one instead of atom optimizer, which is really a variation of stochastic gradient descent. I'm going to go with stochastic gradient descent. I'm going to give it a manual learning rate of 1.1. That's a step size to start with. And actually, this isn't adaptive, so it's going to be stuck with that step size. This one does have some momentum I can specify for it. So I'm going to try some momentum here. So we're just trying a different optimizer where we're at it. It's easy to try these experiments in Keras. Okay, otherwise we're doing the same thing we did before, except we're going to try with a smaller batch size because, well, why not? We're changing a bunch of things up. As a matter of fact, we're changing so many things up that if we were really trying to be systematic here, we'd be probably confusing ourselves a good bit. But I did a lot of experiments in the background, so I have some suspicions that this is going to work here. But nevertheless, we're going to try some new hyperparameters here as well. We're going to try a batch size of 32, and I think this is going to learn so much faster. I'm only going to guess we can get there by 10 epochs. So we're going to do, we're going to assume that this is going to train a lot faster because it's so much smarter. Well, we'll see. We're going to see right now. We're going to plot out the model accuracy. And by the way, we're going to find out this performs much better. We're now up to 98.7%, but we're actually using a bit fewer parameters. If we look at total parameters here from going through our layers, and the math here is pretty straightforward, we're going to find out we have fewer parameters than we had before, and yet we're getting better results. As a matter of fact, my suspicion that we train up pretty fast here is true. Boy, we really did train up pretty fast here, right? So in many fewer epochs here, we learned a lot faster. But this is more complex learning, so the amount of time it takes is somewhat comparable. But at the end of the day, what we really care about is that we plateaued up here with our testing data to 98.7%. So we did a good bit better. And we're still overfitting in here. We're still not gaining much here. We can keep running this all day long, and we're not going to close this gap here. But we did better overall where it really counts. So let's see our scores thus far. One layer of CNN gets us to 98.7, and that's our best so far, even though we got fewer parameters, a simpler network. So we might be convinced at this point that convolutional approach is pretty effective with images. Okay, so, well, if one layer was good, maybe more is better. So let's try that. It's easy enough to try in Keras, right? So let's take and stick in another convolutional layer right here. And we're going to do that in our second layer. I'm going to decide that I'm going to go with 64 filters in this next layer. It's going to learn even more features. So we're going to go with 64 filters in this layer. We're going to stick with 3 by 3. I changed the dense layer. I'm going to add a few more neurons to dense layer. I think I had 100 before. I'm going to go with 128 now. So let's make this a slightly more powerful network, and let's see what happens when we run it again. And indeed, now we're up to 99%. And so we can see that, we're back up to the same number of parameters I think we had in our largest, regular fully connected layer, roughly the same number of parameters. But our performance is our best so far. We're at 99%. However, we're still not going to do much better than that no matter how many epochs we run this. We're stuck at this kind of level of overfitting. But still, we're up to 99%. And you may be impressed by that because we're probably close to superhuman right now. By superhuman, I mean better than human beings do on these kind of tests. We're in that ballpark right now, but let's see if we can do better. Well, if we want to do better, we have to deal with this overfitting, right? That seems to be in our way. We could just try more and deeper layers and everything, but you might have the suspicion that's going to run into, again, vanishing gradients or something like that. So let's see if we can do something more intelligent or introduce a very important concept, which is some explicit regularization into our neural net approach. We saw how useful regularization was, or necessary it was, in our earlier machine learning stuff. We need something here to deal with it. We know regularization is the way to deal with overfitting. So what can we do here? Well, we can look at a technique that called dropout, which I have the mind blown emoji here for two reasons. One of which is that it seems like a crazy idea that will blow your mind the first time you hear about it. And the second one of which, it is literally going to be blowing the mind, yanking wires out of our network here. So dropout is taking and yanking out neural connections in the middle of training. We're going to take and just grab randomly some neurons in our network and our fully connected layers as we're training and rip them out and see if that will help us. How could that possibly help us, you might say? Well, that's a good question. That's the reason why nobody just came up with it, 30 years ago. Instead, it took until somebody trying crazy ideas and throwing stuff at the wall, although that somebody was Jeffrey Hinton, who has a lot of experience and deep experience in deep learning. In 2012, introduced the notion of dropout, and we'll try that here. We'll see how it works. And once again, the analytical justifications for this stuff are very hard to come by. As a matter of fact, stuff like dropout, it's almost impossible to analyze. It's such a just crazy thing from a mathematical perspective. However, we're not completely at the dark. We're not randomly trying stuff. There are ways to view at it. You can view at it as training set augmentation. We're going to talk about augmentation in another 20 minutes or so. So it's a little forward reference. That's the way I think of it most likely. You can look at it also as ensemble training different neural networks to vote on the same problem. However we think of it, it turns out to be very effective. And so it's a very common way to deal with overfitting. And it's very easy for us to throw that into Tensorflow. Because of course, as soon as somebody comes up with the idea, somebody actually implements a nice user level layer for us to grab. And we can add in Tensorflow dropout to our network. And you might be surprised that we're ripping out so many of the neurons. We're going to rip out a quarter of the neurons in this layer and 50% of them in this layer as we're training. So this is because that's the parameter to dropout, is the number we're pulling out. So we're pulling out a lot of the neurons here in these layers as we're training here. Now, when we're finally done, by the way, so the final actual inference network, the one that you're done with and you test and you use, you don't use dropout. You leave all the neurons that are fully trained. We're using dropout while we're training the neurons to try to help shake things up and get them to close that overfitting gap. So let's try this with these hyperparameters and these layers in here. Let's give it a shot and see what happens. And oh, by the way, as it's training here, it's smart enough to know that when it does the testing, it shouldn't use the dropout. Because again, your final network that you deliver and you want to use doesn't have any of this dropout going on. So when we do our testing, as it's reporting testing along the way, it'll disable the dropout. It'll only use it while it's training. That's nice that it does that automatically for us. So when we do this, we find, wow, this actually, in comparison to has very different behavior in comparison to our earlier attempt here. Definitely closed this gap on overfitting very dramatically. You can see this seems to have a very, very demonstrable, obvious effect on overfitting. So let's look at the specifics of the network right here. It doesn't have many more parameters, right? Dropout didn't cost us much in terms of a lot of parameters to train, nor a ton in terms of training time if you look at the actual time it takes. So it's very, it's not that costly, but boy, it was effective at closing the gap. And as a matter of fact, it got us up to 99.2%, which I do believe is superhuman for this particular problem. So you can see dropout is very effective. Well, again, it's indicative of this field where crazy ideas that are relatively recent, right? Something that's only 8 years old becomes kind of the standard and very important tool to use. That's how fast moving the field is. And there we are. Okay, now these are our scores thus far. This is clearly the superior approach and gets us the best results. But it might lead you into investigating other ways to deal with normalization and or regularization, excuse me. And another thing that people are currently finding to be quite useful in dealing with overfitting issues is to use batch normalization. And that's the idea. I mentioned earlier that biases are kind of nice in that they center our results a little bit more around the activation function. And so they're kind of standard in all these layers here. Well, batch normalization is taking that a step further and saying we not only want to kind of center things, but we also want to normalize the curve. We kind of want to make sure that from one layer to the next, we've kind of got these normalized results to keep things really in the center of activity for these neurons and whatnot. And it's a lot of hand-waving arguments, but it turns out to be effective. And so batch normalization is another way to deal with Also with vanishing gradients, right? Because it makes sure that you've got appropriate values, not vanishing between one layer to the next. Or the corresponding problem you can come upon, which is exploding gradients. That can certainly happen too, especially with functions that are bounded like ReLU. Okay, so let me finish this slide here though, and say that batch normalization is another common layer to add in now to networks to see if it can deal with overfitting and also, like I say, vanishing or exploding gradient problems. Its application is also open to a lot of suggestions as to where it's appropriate or not. People will say it's not compatible with dropout and explain to you why and write papers on it. Other people will tell you it works great with dropout and explain it and write papers on it. Some people say apply dropout only after the batch normalization layers. Other people will disagree with that. So it's a good example of how open the field is right now. Controversial a lot of things are. It's interesting and exciting is another way to think of it. Some people say apply it before or after the nonlinear activation function. That's also open to debate. And if you might say, well, how do I even have a choice with the way we've been doing this? Isn't the activation function embedded in the layer? Well, you can pry apart the layers if you want to. Keras is very flexible and lets you get down to the old Tensorflow 1 kind of levels where you can pull things apart. So here, for example, we can pry apart our layer, apply the batch normalization, and make sure the activation function happens after. So if you want to control the layers at a lower level, Keras gives you that ability instead of what we've been so far, which has been happy with just the defaults. So this is easy stuff to apply, and we can try batch normalization and see how it works. Very easy to test with TensorFlow. We apply it, and we find out that, you know what, for our problem here, it's not a magic answer. It does not seem to be helping us. It gives us, we're not doing our best so far. So it wasn't better than just a dropout. But of course, this is far from an exhaustive test, right? We just tried one thing. We got a lot of hyperparameters involved. Maybe if we used it somewhat differently, it might improve. That's a very valid question. But these things aren't all just magic bullets guaranteed to give us improvement. But it's an important technique that you'll see in lots of current architecture. So I wanted to point it out. Here is a demo that is incredibly insightful into what we've just been doing, all the things we've been discussing. And so I recommend many of you go and play around with this. And so the way it works is that and it's running in your web browser. It's insightful for a number of reasons here, because it not only shows you the techniques that we've been using, but it also shows you the principle that inference, once you've trained a network, it is very lightweight to do the calculations in the forward direction. This is running in my web browser, and if you run it, it will be running in your web browser. It's some crappy JavaScript code, and yet it's able to do what you're about to see, which is in very real time recognize the digit 2 that I've just drawn. See how quickly it recognized that? That's not because it has some powerful back end running somewhere. It's running in the browser. Now, if we look further, the reason I like this demo, it shows us exactly what's going on. This is a network very similar to the one that we just built. Not exactly the same, but close enough, different enough to be interesting. And we can see the input layer going into a convolution layer, then a pooling layer, they call it a downsampling layer here, then another convolution layer, then a downsampling or pooling layer, and then a fully connected layer at the end. And you can see how it went from a 2 here through the convolutions. And if you hover over any of the pixels, it will show you where it drew from. So you can see how these convolutions scanned over these pixels in the prior image. So this pixel came from the convolution over this area of the image. So here's the first layer, convolutional layer of transforms. And if we look at this, you can see that what has been transformed here with each one of these different kernels, again, is no obvious, say, edge detector. There's no explicit edge detector here. Instead, what we've got going on here are some things. This kind of looks like a vertical edge detector, kind of, sort of, you know, I might guess. This kind of looks like it's figuring, this one on the far left, like it's finding bottom edges. So there's kind of some edge detecting going on here, but none of them are as simple as that. It's learned to find kind of edges. And then we see the pooling layer here. This is just downsampling, so this just shrunk everything down. Here are the convolutions in this layer and where they're drawing from. And if we look at these convolutions, wow, I definitely got no idea what they're up to, right? It's hard to even guess what they're up to. And yet they're able to extract enough information to be able to distinguish the important parts of these digits. So by the time they downsample once again and pass it on to this fully connected layer, it's got a lot of high level information. And it can very effectively then, in conjunction with this next fully connected layer, figure out that this is a 2. And you can see the 2 is lit up most highly here and where it's drawing from. And again, this happens in real time. So let's do a new digit here, like a 0, poorly drawn with my mouse, but nonetheless, it's recognizing it. It shows you the first guess is a 0, second guess is a 6, very poorly lit up. So it's pretty sure this is a 0. The value for 6 is, I can't even see it lit up. But again, the filters here, we can look at it and go, yeah, I think I was right. I think this thing looks like a bottom edge detector-ish kind of thing on the left there. And this looks like kind of detecting some side edges. Edge detection, obviously, kind of a useful thing for first layers to learn. So they often do kind of figure that kind of stuff out. But then by the time we get into some deeper layers, I got no idea what it's figuring out here, but it's figuring out useful stuff because it's pretty accurate. So this is a demo. It's very similar to what we've done. Matter of fact, you can with TensorFlow very quickly turn what we've done into this exact model if you wanted to. So go ahead and do that as an exercise if you want. But more importantly, please feel free to go ahead and play around with this. It's a wonderful example of this. When I first stumbled upon this, the guy that did it was hanging around Vancouver, I think, University in Vancouver. And now he's cross campus from me at Carnegie Mellon here. So that was kind of neat to discover by the time I found this. But at any rate, it's a wonderful example of a couple of concepts, one of which, most important one of which, is that these filters are definitely doing stuff, but you can't pry out exactly what they've learned, but they work. And so play around with it and explore this. Okay. And draw European 7. Okay, I'll give that a shot, although you should play with it yourselves. I'll bet that confuses it because I don't think it's trained on any European 7s. As a matter of fact, if I lift up my pen, analyze, let's see if it reanalyzes it. Okay, just 7. Maybe, I don't know if that's because it trained on, I don't think it trained on 7s. I've never seen any of those in the mnist data set. I'm sure they're not there, but it probably was the closest guess. So 3 was the next guess. Interesting experiment. So play around with it yourselves and see if, see if it doesn't give you some immediate insight. So it's a great, great demo. Okay. Now, as I've mentioned several times as we're going along here, TensorBoard is part of the ecosystem, the TensorFlow ecosystem. That's one of the reasons I like TensorFlow. It's got a lot of pieces that have grown up around that are really useful, and TensorBoard ties a lot of those pieces together. And it is a nice utility in a lot of different ways. Does a lot of different things for us. It is easy to use. All you need to do is add into your model when you run it a callback. In other words, telling the model that you kind of hook this feature in to tell it to use TensorBoard. And then what it will do is it will log in real time as the model's running to whatever directory you tell it. It will log this information and get my laser pointer back. I'm never sure if you can see the arrow or not. It will bring back the it will bring back to this directory any real-time data you ask it to record. In this case, we're going to tell it we want a histogram at the very least, and this will run. Now, it's a little bit, at first it seems a little bit annoying in that it runs as a server, so you have to do a couple of extra steps to get it started. In particular, you have to start up somewhere else on the machine, a TensorBoard server, and point it at your log directory, and then somewhere else you can start a browser and point it at that. And again, that seems like a lot of extra steps to get some information out. But the reason for this is that you'll find that where this is really useful when you start doing serious training and your models are running for hours and hours or days, that you don't want to sit there in front of a terminal. Instead, it's nice if you can log on from wherever and monitor how things are going. And particularly when you start doing things like doing hyperparameter searches and whatnot. So it's nice to kind of observe this stuff from afar. And that's why its default mode is this server, its only mode is this server-based thing. So when you fire it up, though, it gives you some really nice stuff. Like it'll allow you to see the graphs that we generated with matplotlib here. It'll spit out for you automatically. And so this is our first 64 wide fully connected model. Here's our convolutional neural net. And it's the same things that we did with matplotlib. No reason they should look any different, but it's convenient. We don't have to plot anything out. It can also allow you, if you inherit some architecture, if you grab some network and you're using it, you can kind of pull it apart and look at it and dive into things like, here's our fully connected thing. We can even dive into the layer and see the operations going on inside of it. We knew that there was a matrix multiply going on in there, and we can kind of see it in a bias add. So it's really nice to dive into stuff. And again, that can be useful if you inherit a large, complicated network. And I'll show you some networks that are quite complicated before we're done here. So that's not a trivial functionality. One of the things that's really powerful, though, is that you're trying to gain some insight when you're training your models as to what's going on, but we have many, many weights, right? We have millions, billions of weights going on. So you can't stare at a given weight and see what's up. And as a matter of fact, these things are all statistical. They're all over the place. So if you want to see, like, are my biases really important? Are they centering things? Are they drifting? You need some high-level statistical views, and those are kind of by default built into TensorFlow as the native way of viewing stuff. So you can see, the biases in a layer here, how they're going over time. You can see histograms, and the distributions and whatnot. So this can give you as much insight as you're going to get into the mysterious workings of a network, which again are statistical in nature. So you can't look at any one given weight and make any meaningful conclusions. There are a lot of add-ons to TensorBoard which are really helpful. I've mentioned to you already, hyperparameter searches really need to be systematically done for anything that's leading edge or complicated, and you can do those in an automated way with TensorBoard. So you can see here it's reporting in real time as a bunch of test experiments are being run with different hyperparameters here. Here it's turning dropout to different values, trying different optimizers. It's reporting the accuracies. It runs through and tests these different things. That's pretty awesome, right? When you realize how tedious the hyperparameter search can be. And performance in general becomes important when you start having these things that run for days or weeks at a time. And you can get some performance profiling out, see where the time is spent. You can even get some low-level stuff and see where the time is spent on the GPUs. And it can give you some insight as to where you might possibly be able to save time. For example, a lot of times people will find out that the I/O time is actually where time is being spent. And that sounds boring and stupid and awful. Like, why is I/O significant? But when you start talking about we're doing batches, stochastic batches of data, right? That means every time you do a new mini batch, it's got to go to disk and grab a bunch of batches out of off of the disk there, and from all scattered all over the disk, and assemble them, pre-process them, right? Because it's coming from disk. By the time it feeds into your model, things might want to be normalized, might want to be converted to fixed point, any kind of low-level stuff that's going on, and all of that kind of stuff can take a tremendous amount of time to where it's taking up a majority of the time. And if you can pipeline that, there's no reason why the CPUs can't be going off and grabbing stuff from disk while it's already processing the current mini batch of data. And so anyway, those kind of things can be pipelined and be very effective and work well. And performance profiling can allow you to uncover that and decide where to apply those kind of optimizations, or where to at least ask people to help you out with this part of your code. So that's really nice stuff. Scaling up beyond one GPU has also gone from being a curiosity that only people on the leading edge did to being something that everybody's doing now, because it's become the norm. So if you want to do really leading edge work in any established areas of machine learning, you might find yourself having to use multiple GPUs to get to leading edge size models. And so multiple GPU use is these days enabled pretty well by the frameworks. Originally, people would do simple brute force things like train 10 GPUs with the same, with the same data set, and rely on the fact that they're all starting out randomly, initialize randomly, to figure that you're basically training 10 different networks. And then when they all look at a digit, you can take the vote from those 10 different networks, and that ensemble approach is going to be more accurate with them all voting on things, the wisdom of the mob, if you will, right? And that will work, but that's undesirable in the sense that I don't want to have 10 GPUs to identify a digit. I want one really smart network. So how can I get 10 GPUs to train one smart network? In other words, I want 10 GPUs working on training to get all their power harnessed, but I want them to deliver one small set of one GPU's worth of weights when we're done. And we can do that by making sure that they're all using the same weights to train. And you might say, well, if they all use the same weights to train, then they're all going to be doing exactly the same stuff. No, they use the same weights, but they all train on different data. And so we can have, say, 3 GPUs here, and they all grab a different chunk of data. They start out with the same weights. They all train on a different chunk of data. And then when they're done with that training, with that mini batch, they all want to push the gradients, the weights, in a different direction. Well, now we can use that wisdom of the mobs ensemble approach and have them all average the weight that they want to adjust the weights. So we get 3 GPUs voting on which way to move the weights. After they figure out how they on average want to move the weights, then they all agree and synchronize and use the same weights on the next pass. So they're all using the same weights, training on different data, and then averaging their gradients when they're done. And that's a powerful way to scale your problem up, so it uses a lot of GPUs to speed things up, but at the end, they still deliver you one GPU set of weights to go and move into the real world in your application. So you want a whole data center to be training your self-driving car, but at the end of the day, you want your self-driving car to just all fit on one GPU inside that car as it's driving. And so this scaling up approach, there's several ways you can do it. TensorFlow has built in a mirrored strategy approach, which is pretty easy to incorporate in, and then it will hopefully distribute things across all the nodes. And it does indeed work. An extreme you can use at very large scale. People have found that very large scale, when you're using thousands of GPUs, that it was necessary to optimize things even further because mirrored strategy wasn't quite optimized to work across huge networks with thousands of GPUs. It may get there, but at the moment, Horovod is a nice plugin that you can easily use. A plugin, it's kind of an API tweak you can hook into Tensorflow and easily use. It's not complicated. So here's an example of how to plug it in. You just need to add a few hooks in, and then it scales up across many thousands of GPUs. As a matter of fact, here's an example of it running on Summit. Is that where this ran? I think this ran on Summit on 27,000 GPUs. And it was used to do a kind of a hurricane prediction model, weather anomaly prediction model, cyclones and atmospheric river events. And as sophisticated and leading edge as this is, I think all of you now are capable of understanding the pieces that make it up. If we look at this, we've got a bunch of convolutional layers and some dropout layers in here. I think mostly convolution. I see mostly all convolution, a bunch of convolutional layers, and eventually going into a fully connected layer. And that's it. That's all it is. So you're capable of understanding some fairly complex networks right now. The interesting thing about this is not only that it runs on 27,000 GPUs at over an exaflop of performance, but also that it is very accurate. And at first, that might not seem hard to do because when we talk about predicting hurricanes with accuracy, if my hurricane predictor just says no hurricane today, that's all it ever says. It's just a piece of paper that says no hurricane today. That algorithm is 99% accurate because most days there's no hurricane, right? So instead, you need to start to scale and weight your input data to penalize greatly results that are false negatives for hurricanes, right? Otherwise, the error rate starts out low by just being very dumb. And so this is where you want to start involving weighting techniques, weighted loss functions, and weighting your data sets. And so it's another important area to be aware of in machine learning, especially if your data sets are highly biased. Another way to deal with increasing your data sets, though, and make them better is data augmentation. And this is very important to the point where today almost no paper about GPU learning doesn't have a little paragraph describing how they augmented their data. As we said, supervised learning like this, meaning where all of our data has to be labeled, our training data has to be labeled, is typically expensive to get. Even with mnist, right? Some poor grad students had to label all these images with, say, tumor recognition, something a little more leading edge. Somebody to train things to recognize tumors, some human had to go in, some radiologist had to go in and label the tumors. And that's no fun to do and expensive and tedious. So getting thousands and thousands of tumor images is not easy, right? So getting labeled data is expensive, and you don't want to waste it. And we talked earlier about that tension between training data and test data. But one way you can help that situation out is, what if there was some automated way we could take and make more data in an automated way? It doesn't involve a human. Well, one thing we can do to get more data is we can start to muck with our data in ways that also will improve our training. Our model can learn to be a little bit better with rotation invariance or scale invariance or muddy digits. Our mnist model was only trained on these nice upright scale digits. It's going to be pretty poor at recognizing digits that are rotated. It hasn't seen them. It hasn't learned on them. It won't just magically get that. So if we want it to improve its training, we can take and automatically go and rotate all the digits to varying degrees. And we can make this automatic because the labels come along with them. We know it's a 4. We can rotate all our 4s and keep them labeled as 4. We can shrink them. We can add noise to them to make things fault tolerant. So we get all of this kind of for free. We can amplify and improve our training data. So data augmentation is really important. With convolutional based things, you might not even have to train, interesting experiment for you to try, for translation invariance, because convolutional based things, by the very fact that convolutions are scanning over the image, they generally have some pretty good translation invariance automatically. If they didn't, we could certainly translate things around that, augment things that way. Anyway, this is a very important thing to do, and you could easily come up with a workflow pipeline that involves, Photoshop batches or some nonsense like that. But because this is so common, TensorFlow has rolled into it the TF image, methods which make this stuff pretty convenient. And if the things weren't in there that you needed, again, you can come up with lots of workflow pipelines that augment your data. Okay, I've mentioned several times already that the main competitor, if you want to think of a competitor or alternative, I think the only serious alternative to TensorFlow would be PyTorch. And again, it's a fair balance between the two. I picked TensorFlow for some reasons I highlighted. But if I use PyTorch today, it wouldn't be drastically different. And as a matter of fact, I hope that because the two have converged. TensorFlow used to have a less user-friendly front end and be lower level. Now with Keras, it's very friendly in the front end. PyTorch used to not have a layer-based approach. It absorbed Caffe and is now more layer-based approach. And so these days, there isn't a huge difference between the two. And here's an example of our mnist with convolutional and layers and dropout and pulling here. And I think you probably don't find this to be incredibly difficult to understand what's going on here. You can define the layers pretty straightforward. These are the forward layers defined. There's a lot more on this particular example, so don't think that this is a lot that PyTorch has a lot of extra nonsense. This example is has a little bit more flexibility. It takes some command line arguments and will automatically configure some stuff. So it's got a little more nonsense built into it. But the crux of it, the real core of this is, hey, you can define the layers in a very easy, straightforward way to make a network. And so it's not that different from PyTorch in that sense. The two have grown together. You can get this example here if you want to play around with it and see. Exercises for this stuff. We have at our fingertips some very, very easy exercises sitting around in the Keras data sets. It's another reason I like TensorFlow for this stuff, is that we have besides the mnist data set, we have a bunch of other data sets sitting around. The fashion mnist data set would be the easiest one to move right from what we're doing right now. If you want a more challenging problem, but one that's not too much of a leap, you could use the fashion data set, which is 60,000 training and 10,000 test images of 10 types of clothing. They're 28 by 28 grayscale images, right? So this is a very similar data set, only it's a little bit more challenging here. We're trying to recognize clothing types. And so you can just grab this data set, plug it right into what we're doing, and go ahead and train and see how that works. Okay, as I said, PyTorch, fun way to go. Here we are with the fashion mnist. Is a very simple exercise, very similar to what we're doing, very little to change to go ahead and use it. But built into the mnist data set are also some other different things that we can do. Answering your earlier question, do neural nets do things besides images? Well, right away, we can see that we can do kind of things like regression, things like predict housing prices. That's built right into the mnist data set. Here, the image stuff does scale up to the more complicated stuff. So CFAR 100, we can do 32 by 32 color images, 10 classes, or CFAR 100, which is 100 different classes. That's the difference between the two. Here's semantic analysis, Internet Movie Database. Are these reviews good or bad kind of thing? So that's more semantic analysis, natural language processing oriented kind of stuff. Reuters Newswire, same category. So these are right there in mnist, right there in Keras for you just to grab and use. But more exciting, I think, if you're interested in learning and growing with this stuff, is the fact that this established method of having standardized data sets that people use competitively, even in the academic sense of how do we quantitatively compare our performance, all the way up to the money competitive sense. This competitive notion in machine learning, which neural nets have definitely consolidated around, is awesome. And it has resulted in lots and lots of standardized data. And in particular, there's a fantastic website that consolidates a lot of this, kaggle.com. And if you go there, you'll find over 20,000 data sets, incredibly diverse across many, many different domains. So again, the question of are neural nets used for other things besides images, you're going to find incredibly diverse kind of things there, many of which are image-based, of course, because neural nets are great at that. A lot of the world's image-based, but lots and lots of other very non-image things. And you'll find lots of data sets there if you want data sets, and lots of competitions. It's really amazing what's going on there. So for example, when I grab this snapshot, if you could do steel defect detection, you could win $120,000. 300 teams competing for that money. Very competitive, very interesting stuff. Lots of competitions going on there for some serious money. Lots of teams competing at any point in time. And as a matter of fact, you can even find digit recognition going on. When I snapshot of this, and probably most of the time, no money for that one, but a lot of teams. And you can see the winning, algorithms and their results. So it is not at all, I'm glad to give you some exercises like on a previous slide to work with, but even beyond anything I can give you, I encourage you to go and grab something from your own area of interest, whether it's just enthusiasm or whether it's applicable to the domain that you're really interested in developing an application for. The data sets are there. The examples are there from people's winning problems and winning solutions. So there's tons and tons of fantastic exercises that should hit you right on the head for whatever interests you. That's a great place to be, right?